It is an automata which don't have any secondary storage. That is, it cannot remember the portion of the string which is already recognized. That's why it is called second limited memory automata or acceptor. So it is broadly categorized into deterministic finite acceptor and non-deterministic finite acceptor. We will discuss about these two acceptors broadly, but first of just let's discuss how we can represent a finite acceptor. There are three ways we can actually represent a finite acceptor. The first one is transition function. The second one is transition diagram. It is a diagramatic representation of finite acceptor. And then a transition table is a tabular representation of different operation and different transition from one state to another state explained in table form. But first, let's explain the important element in the discussion of finite acceptor is what a state. So how we define a state? State mainly represents the value of the system at a particular instant of time. So what happens, we always define a state with which is different from the previous state upon accepting an input. So its state changes from time to time. For example, think about any physical body. At the initial state, it is cool. Now, if we provide an input like heat, its temperature goes up. So its state changes from cool to hot. So that's why, same way, this physical phenomena can be modeled using a symbolic representation of state, which will be we using broadly throughout our design of finite acceptor. So let's come to the formal definition of what is deterministic finite acceptor. Actually, it is mathematically represented using quintable, which is consists of q, sigma, delta, q naught, and f. And I'm going to describe each one exactly what they are. Q is a finite set of internal states. So I have already defined what is state. So if I think that system goes one state to another state upon accepting a symbol, so all the states during the process of accepting a state can be think of it as set. Then sigma is all the permissible input system in the process in a finite acceptor called represented by sigma. Delta is the function which I have already talked about, the transition function. It is actually takes two input, one input from input symbol set, and another take input from the set of states, and provide a state which is the next state in the sequence. Q naught represent a starting state where from where finite acceptor will begin its journey, and the F represent the set of final state where the journey of the finite acceptor will end, and it will precisely say that whether a provided string is accepted or rejected by the finite acceptor. So the definition for NFA or non-deterministic finite acceptor only changes at the place of transition function, where input symbol for the transition can be an empty string or any valid input symbol, and it it can go to more than one state, which will be maximum by 2 to the power q. Q can be thought of as the cardinality of the set q, or we should write like this. It will be better represented. In transition diagram, the state is represented by the symbol, a circle. Initial state indicated by some arrow, and the final state represented by double circle. And a transition is represented by an arrow. The face of the arrow will indicate from which state to which state it will go upon accepting a symbol. So you can see here an example. This particular example, the final acceptor can accept only one A, or any sequence B then A, or any. This self loop represents the states where upon input accepting the input symbol B, it will go to the same state. Okay. Then the Q1 is a final state, so only single A can be accepted by this acceptor, or series of B and series of A also possible. Then after A, we again can read B. So this way a normal finite acceptor can be represented. The second process is to use the transition function. The delta is our transition function, where we use the first parameter, the state, current state mainly, and then the input symbol. So from current state, taking input symbol A, it goes to Q. You can verify it from the transition diagram. Then the next transition for the input symbol B is from current state Q naught, taking B, it goes to Q naught. From current state Q1, from taking symbol A, it goes to same state Q1, and B, it goes to the initial state Q naught. So this is the way we represent our finite acceptor using transition function. So transition table is very helpful. We will see while we convert an NFA to DFA. It helps to identify uniquely the states. Here the first column shows all the states. So for the starting state we have to use array, and the final state we have to use star, and the input symbol would be the first row of the table, and then below that label we represent transition upon taking the A symbol. So from Q0 taking A, it goes to Q1. Now again from Q0 taking B, it goes to Q0, and Q1 from input symbol A, it goes to Q1 itself, and then again B goes to Q2. So these are three ways we represent a transition diagram or finite acceptor. So all the strings that is accepted by a finite acceptor will constitute a set, and that set we'll call the language. And we always say like that, the language accepted by a finite acceptor like this way. Just like for example, for the language L, A to the power n, B to the power m, where a and m may be 0 or greater than 0, or m n greater than 1, m greater than 0. 0 greater than equal to 0 indicates that this acceptor can also accept empty string, and in this case it will have to at least accept one A, and B can be 0 or more than 0. So let's start with a very simple NFA designing, where we have to design a NFA which accept string like 001. It's a very simple design. So first of all, we have to think that how many states will be needed for the design. For 3 symbol, always remember that the unique number of letters and symbols which is to be accepted, at least the number of state will be the +1 for the number of symbols. For here we have to at least accept 3 symbols, so we need to have 4 states, and we can easily say that for the number of the unique symbols are 0 and 1, and the final state will be Q3. So for the transition function, the process will be for Q0 it will go to Q1. For Q1 it will taking 0 it goes to Q2. From Q2 taking 1 it goes to Q3, which is the final state. For transition diagram, we start Q0 and we put the arrow as we go along to accept a string, and at Q3 we get the string accepted. In the transition table, we use the same thing, that 0 1 symbol, input symbol, and this first column represents the states. We start with Q0, then taking 0 it goes to Q1. For symbol 1 it goes to nowhere, so we use a blank symbol. Then Q1 it goes to Q2 for symbol 0, symbol 1 it goes nowhere, and from Q2 again to blank, Q2 Q3, Q2 to nowhere. So this way represents a acceptor for a given problem. Let's take another example where I have to design a final acceptor which take string like 101010. So that means that number of 0 and number of 1 will be the same. So again we start with transition diagram here. So start with initial state Q0, take a transition from Q0 to Q1 with 1, and again Q1 to Q0. So we always have Q1 to 101010, this type of sequence, so it will be accepted. So again we can go lambda transition to Q0, and again from Q1 to Q2 taking any number of 0 and 1. Yeah. So one can say that this portion can be unnecessary, and we can only take these first 2 states for our purpose. So for above, this NFA can be represented as a language like 0n to the power n where n greater than or equal to 0. So in this case, a particular this acceptor can accept without taking any input. So that's why we have taken this condition also equal to. So lambda in NFA system, we can have a transition without taking any input symbol. So that kind of transition is called lambda transition and represented by a lambda symbol. We already have studied that what is transition function. So in normal transition function, we take one state, which is a current state, and take input, any input, A, B, C, or 0, 1, anything, then goes to the one or particular subset of the states. In an extended transition setting, which is represented by delta star or delta cap, which start with always initial state, and W is the string to be accepted by the acceptor. Now this transition function will generate all the possible states that the final acceptor can produce for accepting or rejecting string W. So that's why I call extended, because it will generate all the states in the process at the same time. Let's take an example here. Here it has some transition, lambda transition also, and for single input symbol it goes Q0 to Q1. So in transition function, for input symbol data or string of transition delta lambda, for the extended transition delta function will produce Q0 and Q2, because from Q0 there is no state for input symbol, and Q1 to Q2 and Q2 to Q1. I already told that all the possible state will be generated. So here for Q1 there is only transition function, transition from Q1 to Q2. There's a Q2 is included, and from Q2 to Q0, so Q0 is included here. For a input symbol AA, it will include all the three states. So this is the extended transition function. This is an example of standard DFA, where making one of the four states a final state, different types of string will be accepted by this acceptor. Suppose we make Q0 as the final state, so even number of zeros and 1 will be accepted by this acceptor. If Q1 is final state, then even number of zeros and odd numbers of 1s will be accepted. And for Q2, odd number of zeros accepted and even number of 1 accepted. And Q3 is final state, then odd numbers of both zeros and 1 will be accepted by this DFA. So we can use this diagram or this acceptor for these types of variation of zeros and 1s. So this type of term will be we always encounter throughout the final theory of automata, that which types of DFA is accepted by the language which is built upon the input symbol sigma. So if you represent the DFA or NFA whatever by the quintuple, then language that this automata is accepted by symbolically or mathematically can be represented like LM, and within the bracket generate all the strings for which the extended transition function will generate the final set of states. And eventually we can say that the language does not accept the string will be the complement of the language of N. All the string which will not be accepted by the acceptor. An important state in the deterministic finite acceptor is the trap state. It is a state if it is entered, then it will not goes out. That is, it will be trapped for infinity time for any input symbol it takes. In this diagram, we can see that the final state Q1 it takes a transition from Q1 to Q2 for input symbol A B, but upon reaching a Q2 it is stuck there, so there is no transition from here. So it is a problem of deterministic finite acceptor because there is no existence of lambda transition in DFA. For the NFA, we can have a lambda transition and can go out. So there is no concept of trap state in NFA.